Professor, Department of ECE, KSR College of Engineering. So now we discuss about the introduction to digital signal processing. So first, before we going for digital signal processing, we have to know about the signals. So the signals are classified as a analog signal processing and digital signal processing. Whenever the analog signal processing gives the accuracy, but here we use the discrete components and the implementation level is more complexity. So these are the problems we have to move to the digital signal processing. So in that one we use the ADC, analog to digital conversion technique. So the analog signals are converted into binary values, nothing but digital values, by using the sampling. First we have the analog signal is given to the sampling, then the sampling signal is given to the quantizer. The quantized signal is encoded with by the encoder, then the signal is converted into binary sequence of data. So why we convert the analog signal to digital means the execution of complex non-linear operations and advanced encryption capabilities and high efficiency data compressions. So these are all the parameters are used for the digital signal processing. So for that, the DSP allows a physical system to be updated purely via software modifications, offering the extreme precision and absolute impunity to the component, and also it referring with the thermal drift and aging. So next we have to move to the continuous signal processing versus digital discrete time signal. So in continuous time signal, so where the independent variable time is varies with respect to continuous instant of time. Next we have to move to the discrete time signal, the x of n, where the independent variable n and the discrete integer value indicates the integer time signal is fundamentally just a harder sequence of real or complex numbers stored in the memory. So now we have moved to the sampling. So what is meant by sampling? The signal is the continuous signal is converted into discrete time signal to process the real world analog signal to a high speed processor or microcontroller. We must extract the discrete component from the continuous workflow. So in this, when we go for the sampling, the continuous sampling interval is shown here. So the density of the sampling point is determines whether the true shape of the physical signal is preserved or irreversibly lost. So next we apply the Nyquist-Shannon sampling theorem, state that the continuous sampling limited analog signal can be perfectly reconstructed from the discrete samples, and if it is the condition is meets, the Fs is greater than or equal to 2Fm. So the Fs is a uniform sampling frequency. The Fmax is a maximum frequency component of the analog signal. So here we have to apply the Nyquist state. If we are not able to satisfy the Nyquist state, the signal may be lost in reconstruction part. So this is the optical illusion for undersampling. So here the example is given here. Here the amplitude of the signal is 1 amplitude and the time duration up to 1 second. So here the true signal frequency is 8 Hz and the uniform sampling rate is nothing but 10 Hz. So this is the when we clearly explained with respect to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16 approximately it have the 16 full cycles. When we applying the sampling converted into a one single cycle. So this is the preserved signal into 2 Hz. So because the Fs is 10 Hz, it is not strictly greater than 2 Fmx, nothing but 16 Hz. The high frequency components overlap and corrupt low frequency components. So it may create some aliasing in the signal transmission. And also when we discuss about the signals, we also know about the properties of the signal, nothing but periodicity, total energy, average power. So in periodicity we have to find the fundamental periodic, unlike continuous sinusoidal signal, and if it is a periodical only if the digital angular value omega is a rational multiplier of pi. So nothing but omega divided by 2 pi is equal to m divided by n, where m and z is n is equal to z. So to measure the total squared magnitude over the infinite time, so E is equal to summation of n equal to minus infinity to plus infinity modulus of x of n square. So another one property is here average power. So the P is limit k equal to infinity 1 divided by 2k plus 1 summation of n equal to minus k2 plus k modulus of x of n square. So it is used to measure the rate of energy delivered over a time. So next we have to move to the system architecture. So in the system architecture, the data is in the form of input side is a discrete signal. Finally we get the output in the form of y of n. So the x of n and y of n. So when the output impulse response y of n is equal to t of x of n, or y of n is equal to transformed into y of n. So nothing but the system is an entity in the process of input signal according to the predefined set of operation rules to yield a transformed outputs. So these are all the system properties, nothing but linearity, time invariance, causality, BI/BO stability, nothing but BI/BO is a bounded input and a bounded output. So in linearity, a into x1 of n plus b into x2 of n is equal to a y1 of n plus b into y2 of n. So nothing but here it will be satisfying the homogeneity and additions. Here no scaling or mixing distortions are affected. In time invariance, the structural property does not drift over a time. The delay is yield identical delay out. It is a causality, nothing but they cannot anticipate the future. The real time physical system must be strictly be a causal. Nothing but y of n depends only on the x of k for when k is less than or equal to n. So the boundary input and boundary output prevents the interval signal from the diverging or saturating hardwares. So next we have discussed about the LTI system with the convolution. So here the LTI system which is satisfying the linearity and time invariance, we determine the result nothing but the y of n is equal to x of n multiplied with the x of n. When we go for the time domain and frequency domain representation, the summation of k equal to minus into plus infinity s of k into h of n minus k. So here the LTI systems are unequally is fully defined uniquely defined the impulse response h of n. If you know h of n, you know exactly how the system will be reacted to any system. So this is changing the mathematical lens with respect to time and frequency. In time domain view represented in x of n, and the frequency domain is represented modulus of x of f. So here the sine wave is in the form of different range of amplitude range of the signals. Then the signal is converted into frequency, means whenever the frequency range is high magnitude, it will be clearly specified. So nothing but decomposing the signals into constitutive of sine or cons components to clarify how fast it changes. So here the hidden pattern in the raw temporal waveforms becomes immediately obvious. Future more complex time convolution operations simplify into the straightforward and point-wise multiplication in the time domain. So here to analyze the frequency analysis using discrete time Fourier transform to discrete Fourier transform. In discrete time Fourier transform, they map the finite discrete sequence x of n into continuous periodic function of digital angular frequency omega. So x of e power j omega is equal to summation of n equal to minus into plus infinity x of n into e power minus j omega n. In discrete Fourier transform, the computer cannot process continuous functions, so the discrete Fourier transform samples the continuous discrete time Fourier transform spectrums at discrete frequency points k. So the capital X of k is equal to summation of n equal to 0 to capital N minus 1 x of n into e power minus j 2 pi n k for the k equal to 0 to capital N minus 1. So when we applying the DFT and FFT, the computational operations are differentiate the both types. So in fast Fourier transform, it is highly optimized algorithm to utilize the compute the DFT in practical software implementation. So drastically reducing the computational overhead in FFT. So the without jumping of n square to n into n log to n, the real-time digital systems like Wi-Fi, streaming videos and mobile networks would be computationally impossible. So we have to move for the fast Fourier transforms. So next, these are the applications for the digital signals processing. So the audio and music processing have the high fidelity equalization, echo synthesis, MP3 and AAC compression, active noise cancellations. In digital image and video processing, the spatial filtering and computer vision edge detection, JPEG and streaming codecs. In telecommunication systems used for high speed modulation, multipath adaptive filtering, software defined radio and OFDM. In biomedical engineering, the environmental noise filtering for ECG, EEG diagnostics and cross-sectional images to reconstruction for advanced MRI and CT scans. So this is the full journey of the transformed signal ACF. If we have to get the signal from the continuous acoustic wave is act as a physical source and it's given to the ADC, nothing but analog to digital conversion. So we have to apply the Nyquist limit fs greater than or equal to 2fm. Then the signal is given to the processor with the condition of LTA system with the convolution either or FFT, transformation techniques. Finally, the signal is given to the real-time applications, the filter, compressed and analyzed data. So in the digital signal processing is an invisible mathematical architecture translating the continuous physical world to an algorithm of the future. So thank you.